Okay, so we're going to start today just sort of introducing ourselves to some basics. Algebra 1, again, the idea behind algebra is it's our way to sort of model a situation, right? It's like in what you'll find in geometry next year. It's kind of the same deal. In geometry, we use shapes to help us model different things, to help us find angle measures and things like that. Algebra is the same thing. We want to find some way to model a given situation when we don't know a particular value of something, right? I mean, that's the point, okay? And so in order to do that, we're going to talk about variables and expressions. And a lot of the terminology that we're going to use, the language that we're going to use, you guys need to hang on to. You need to know what an expression is, because when your Algebra 2 teacher starts talking to you about simplifying the expression on the right-hand side, you want to know what in the world an expression is. So we'll talk about what expressions are. Then we'll review order of operations and then talk about real numbers. There are different numbering systems that we use for different things. And we'll introduce what are called real numbers, which may be a new concept for you, and then talk about the number line. Okay? And I'm going to tell you right now, I've taught geometry for several years, and so I have a pretty good idea of what you guys should know walking into a geometry class. I've never taught a 7th grade or 8th grade math course, so I don't know which of this stuff you've seen before, so I'm going to kind of talk to you like you've never seen it before. If you have, just bear with me and we'll get through it, right? So the deal for today is we're going to talk a little bit about how to write algebraic expressions. And that's just us modeling a situation using some variables and some numbers. Then we'll talk about how to simplify those expressions and talk about exponents and how to treat those. Review our order of operations, and then also talk about square roots, okay? And that kind of thing. So that's what you should know by the time you leave today. Okay, so some vocabulary for you. Number one is a variable. First thing is a variable. What in the world is a variable? Why do we use it? A variable is simply a symbol, and it's usually a letter. Okay. It doesn't have to be a letter, by the way, but it usually is. Most commonly, we use what as a variable? You'll see most often using an X. Right? I've certainly seen my share of equations that have used dollar signs. Right? Ultimately, anything can be a variable, but usually they're letters. As a matter of fact, as you progress through your high school career, not only will you see English letters used, but you'll see Greek letters used, right? Stuff like alpha or theta, as I get used to writing with these things. Right? Those get used a lot. Beta. Okay? But anyway, it's our way of saying, I don't know what this number is, so I'm just going to throw something in its place. Okay? And so that's what we're talking about when we're talking about a variable. Okay? And so therefore, algebraic expression is a combination of, possible combination of variables and numerical values. And so it's a mathematical phrase that includes one or more variables. And again, anytime you hear the word expression, it's just a phrase. It's just a short phrase. Right? Not a complete sentence, just a short phrase. Okay? That includes one or more variables. Okay? Some more vocabulary for you. Exponent. Right? Because I've heard of an exponent before. Right? So the exponent tells you how many times to use the base as a factor. And factor is one of those words that we tend to lose sight of in meaning as we progress through high school also. But a factor or factors are any two quantities that we're going to multiply together. Okay, if you want to factor a number, then you're breaking it down into two or more numbers. If you multiply them together, it gives you that number. So an exponent tells you how many times to use the base as a factor. And so I'm going to add a little bit of vocabulary for you here, just because, again, never quite sure. This is your exponent, right? This is your base. Okay? So, 2 to the third power tells you that we got to do 2 times 2 times 2. And 2 times 2 times 2 is what? No, you went too far. Right. 8. Right? 2 times 2 is 4 times 2 is 8. Okay? 2 to the third power, also called 2. What's the other word we use for that?
Cube.
Yeah, 2 cubed. Good. 2 cubed, just in case you ever come across it. 2 cubed. Okay? Now, when we're dealing with algebra, we're dealing with equations, we're always using what are called inverse operations, right? When we're solving, we're always using the inverse operation. What's the inverse of addition? Subtraction. Inverse of multiplication? Division, right? Everything has an inverse operation. Okay? Everything has an inverse operation. And for exponents, that inverse is a root. Okay? Square root, the most basic of those, is a number. I'm sorry, the square root of a number is a value that when you multiply it by itself, it gives you that number, right? So in other words, it's our way of undoing exponents. So if we do 2, say, squared, what's 2 squared? 4. If I wanted to undo that, if I wanted to perform the inverse operation to get from here to this base, then that's where your square root comes from, right? So the square root of 4, right, is that value, if you multiply it by itself, will give you 4. So it's 2. Okay? Interesting side note here, too. I found this in the class earlier. And again, this falls in the category of, I don't know what you should and shouldn't know just yet. Okay? Right? This is obviously your square root symbol. The big thing is, what happens to the square root symbol when you actually perform the square root? Right? And I see this in all ages. Even my AP stats class, I get this question. I got that question some in the last 4 years, right? Inevitably, when we start seeing these square roots in an expression or an equation, and it's time to take the square root of that number, there's a huge tendency to say the square root of 4 is the square root of 2. There's going to be a tendency to want to leave that square root symbol in there, right? But square root symbol is like anything else, right? When you perform the operation, the symbol goes away. I just want to throw that out there. Okay? All right. Any issues so far? Good? Okay. Algebraic expressions. We want to be able to create these algebraic expressions. We can't use algebra to model something unless we know how to take some verbiage or some English language and turn it into a mathematical sentence or phrase, right? So, what words would you come across that would tell you you're supposed to be adding some things together? What words mean add?
Plus.
Plus, sure. What else? What else would tell you that you're supposed to be adding 2 things together? Okay. Add. Yeah, sure. Okay. Pretty straightforward. What else you got? Say it again. Within?
More than.
Oh, more than. Yeah, great. More than tells you you're supposed to be adding. Some is another great one, right? It's the actual name of the answer you get when you add 2 things together. Those are great. Okay. Some plus increased. You ever hear the word increased? Okay, 5 increased by 3. How would you figure that out? Well, just add 3 to 5, right? Good. What about some words that make you think you need to be subtracting?
Difference.
Difference. Perfect. Okay. Okay, what's the difference between my height and the height of Shaquille O'Neal? Well, Well, if you want to know, subtract our heights, right? Yeah, what else you got? Less, yeah, less or less than. Yep, that works. I've got 2 pencils less than, tell me your name. Spencer. I've got 2 pencils less than Spencer. I just subtract 2 from however many Spencer's got. Minus, sure. Right? I think we kind of hit most of them there. Decreased, right? If you want, again, since subtraction is the inverse operation of addition, increased means add, decreased means subtract. So good. What about multiplication? What words make you think you should be multiplying things together? Yeah.
Multiply?
Yeah, sure. Multiply 2 and 4. Multiply x and 3. Okay. What else you got? Times. Yep. See the pattern in the first 2. The answer to an addition problem is called the sum. The answer to a subtraction problem is called the difference, right? The answer to a multiplication is called product. Good. So times, product. Anybody think of anything else? Those are pretty good ones. Your standards there. Okay? Product times multiply. So we got addition, subtraction, multiplication. We're missing division. What makes you think you should be dividing? Yeah, sure. Divide. Yeah, it's the word divide. X divided by 2. Okay. What else? Yeah. Yeah, kind of the same thing, but yeah. What's the answer to a division problem? Anybody remember? It's always a hard one to.
Quotient.
Yes, quotient. Okay, good. Quotient, divide, divided. Divisible works too. Yeah. Okay. Those words are going to help us write our expressions and get us to a place where we can model some of these situations and get us to a place where we can create some equations and solve some things. Okay? Good. Oh, I forgot you had 2 more signs. Obviously, that guy is less than. Next sign tells you it's more than, right? Greater than, more than. If you want to, you can add the teeth. I can't remember how old I was when I was allowed to stop adding the teeth for the crocodile, right? Took me a while. It was like middle school. But there you go. Less than, greater than. Okay? So let's try. Let's try turning some of this verbiage into some algebraic expressions, right? So first one, write this mathematical statement. Write the mathematical statement for each verbal phrase. We said 4 plus a number. It means you want to do what? Add. So what's that going to look like?
4 plus x.
Sure. Four plus x works. Anybody write it a different way? Sure. That'd be okay, right? Because addition's commutative. Doesn't matter. 2 plus 4, same thing as 4 plus 2. Okay. Sure, that works. Okay. Take a second. Try the next 3. See what you come up with.
Oh, they just like
Okay. Yeah. So some key words there, right? Times, more than, but you had the plus in there, which was good, right? I'm going to try to get you guys into the habit of thinking something along the lines of, if you see more than or less than, then you're going to want to flip-flop those 2 values, or vary, if that makes any sense, right? Only issue is because obviously with plus it doesn't matter. But with subtraction, it does, right? So 3 more than the quantity 5 times the number. Well, the way I see this is I don't know what to take 3 more than of until I figure that out, right? So the first thing I got to do is figure that out. So the first thing I want to do is take the quantity 5 times the number n. Okay? So if it were me, I would have written it 5n. Okay, now that I know what 5n is, I can add 3 to it. So now I can add 3. Again, with plus, it's not ultimately going to matter. But with subtraction, it is. Okay? So just some other ways to kind of avoid any hang-ups down the road. Okay, good. Okay. All right. The last 2 less than the sum of 6 and a number m, right? Jade. Okay. Tell me how to write 2 less than the sum of 6 and a number m. Oh, I keep forgetting. 6 plus m minus 2. Good. And obviously, again, just to beat a dead horse, because I like to, I guess. Obviously, we're not going to do this. That's very different. Right? So be careful about getting into the rut of just writing left to right. Okay? If that works. I don't know what to take 2 less than of until I figure out what the sum of 6 and the number m is. So I got to do that first. And then subtract the 2. Does that make sense? Any issues, questions there? Okay, cool. Moving on. Order of operations. Anybody never heard of order of operations before? Right? Good. Order of operations tells us in what order we should be performing things. Right? The issue here is if we didn't know order of operations, or if we didn't want to apply order of operations, we can get into some trouble. Right? For instance, what's 6 times 3? 18, right? It's 18 minus 2. Okay? Great. Think about it another way. Doesn't matter, right? What's 3 minus 2? 1. What's 6 times 1? So is this 16 or is this, oops. What happened? What happened? Oh, there it is. Okay, good. So is the answer 6 or 16? I mean, that 6 times 3 minus 2 can't represent 2 different numbers. Doesn't make any sense. Right. So you guys are right. Obviously, it's 16. Okay. So without order of operations, we get into a lot of trouble. Right. We start finding incorrect values. So how does this work? Well, the very first thing you need to look for and work out and simplify when you start simplifying expressions is anything in grouping symbols. Okay. Like what? What are grouping symbols? Parentheses. The only grouping symbols we have, or are there more? What else have you seen grouping symbols? Yeah. Brackets, sure. These guys, right? What else? You see anything else? We'll use some things. Maybe you haven't seen them yet, but sometimes braces. Those things. Okay, I'm running out of room. Let's get rid of this. You guys know what absolute value is? Right?
2 nines.
Right. It's 2 bars. We'll use absolute value as grouping symbols sometimes. Okay? That may be later on. What's absolute value mean?
How far away it is from 0.
Perfect. And therefore, absolute value is always
Positive.
beautiful. Because I don't think any of you guys live negative 2 miles away from the school. Right? Huh?
What if you live in Sites?
Well, then you'd be 0 miles from the school, wouldn't you? You could try. You could try and do negative distance, right? Ferris Bueller did. You guys seen Ferris Bueller's Day Off? You know what I'm talking about, right? Old movie, but it's still pretty good, right? Ferris Bueller took his buddy's dad's, was it Corvette? I can't remember. Corvette, Ferrari, something like that, for a joyride. He skipped school, took it for a joyride. His buddy's dad was obsessed with that car, so he tracked the miles every day, the mileage on the car every day to make sure no one else drove it. And Ferris Bueller said, that's fine. We'll just drive it backwards for a while, too, and we'll reset. It didn't quite work that way, right?
And then something broke and it went off of like a 3-story building. And
Right. 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 So absolute value is always positive because distance is always positive. Anyway, grouping symbols. And, I'm going to add this in there too. Fraction bar is a sense of grouping symbols, right? And that we're going to want to work completely in the numerator first and then completely in the denominator next and then divide. So fraction bar is a little bit of a grouping symbol. There you go. So the grouping symbols. And then we're going to look for any exponents. We're going to look for any roots and work those out. And then the next line is multiplication and division. If you're trying to decide between multiplication and division, we work left to right. Right? Then same thing with addition and subtraction. When you're trying to decide which one to do first there, just go left to right. Okay? Grouping symbols kind of messes this up a little bit, right? But there's an easy way to remember this. What is it? Right. Right? PEMDAS. P for, it's GEMDAS, really, right? But we always, parentheses is the most common grouping symbol that you'll see. But PEMDAS, so parentheses first, then exponents and roots. It maybe ought to be PERMDAS, I don't know, but exponents and roots. And then multiplication, division, work left to right. Addition, subtraction, work left to right, right? Also heard this morning, please excuse my dear Aunt Sally. You guys have heard that. It's the same thing. Help you try to remember that. Okay? But you got to follow these order of operations, and you got to follow them exactly. Otherwise, you're going to end up down a wrong path, and you don't want to end up there. Right? Okay? All right. So that's going to help us evaluate. Right? It's going to help us to evaluate. Whether it's our expressions, to simplify our expressions, or just with numerical values, completely evaluate and find out what that expression is supposed to be showing us. Okay? So for example, we've got 30 divided by 5 times 3. Got to do what first? Right. Remember, we're trying to decide, the only 2 operations you see is division and multiplication, so we just work left to right. So we're going to take 30 divided by 5 first, which is 6, right? And 6 times 3 is 18. Okay? It can be that simple. Some of the other ones get a little bit more complicated. So let's try some more. And I'll give you some time to work on these for a second. And you're missing some of those values, obviously, so just make sure you fill those in and then work them out. PEMDAS, what we got to do first? Parentheses. Do you see any parentheses? No. Said before, you can kind of treat a fraction bar like a grouping symbol, which means just do all the numerator first, and then all the denominator next, and then divide. So we're going to concentrate on simplifying this and then this, right? What's next? Square root, because the next step is exponents and radicals, right? Okay, so we got to do the radical. We got to do the root, square root. So square root of 4 is 2. Okay. Anything else in that step? Any exponents? Yeah, right? Where? Not in the numerator, right? Either the numerator or denominator. Yeah. You got this guy right here, right? That's an exponent. Remember, anytime that little number is in the top right-hand corner, it's an exponent. So we got to do 7 squared. What's 7 squared? Okay, great. That's that one step, right? And rewrite it. Just don't try to go too far too fast. You'll get yourself lost if you're not really careful. Okay, great. So that's exponents and roots. The next step needs to be which one? Multiply, divide. Do you see multiplication in the numerator?
Yes.
Yeah. 7 times 2. Do you see any multiplication in the denominator? Or any division? No? So you can leave it alone if you want. Okay. Then what's next? Right? Any addition or subtraction in the numerator? Nope. Addition, subtraction in the denominator? Yeah, both, right? So how are you going to do it? You're going to do 49 minus 1 and then add 8?
No.
Okay. You work left to right, right? 8 plus 49, 57. 57 minus 1, 56. Okay? And it would be fantastic if you went ahead and reduced that. Not divided it out, but reduced it. Because it will, right? It will reduce to what? Right, 1 over 4. Yeah. 1/2 would have been 14 over 28. Right. Okay? So 1 over 4. Okay? Any issues, questions there? I think most everybody got there pretty quick, right? How you doing? Okay, good. Let's try another one. Give you a second. If we're starting to kind of get this, we'll maybe skip down to one of the last ones and then move on. Okay, Brooke, walk us through this. First thing you're going to do.
I multiplied 9 times 3.
Okay, good.
And I got 27.
Good.
And then I took 1 over 3 times 27 over 1 equals 9. Oh, no. I did 1 over 3 times 27 over 1.
Okay. 1 over 3 times 27 over 1, which gave you,
9.
okay.
And then I did plus 8.
Okay, good. Keep going. So you got 9 here. So when you multiply these two guys together, you get 9 plus 18, which is
27.
beautiful. Okay. A lot of ways to approach this. If you just knew that you had to find out what a third of 27 was, then that's fine, or however you wanted to write it out, but that's good. 1 over 3 times 27 over 1. Just a quick refresher for your fractions, right? When you multiply two fractions, you multiply the numerators and then multiply the denominators, and then you're ready to rock and roll. So here, 27 times 1, right, is going to be 27. 3 times 1 is 3, and then that tells you to divide 27 by 3. So however you get there, it doesn't really matter. 27 divided by 3 is indeed 9. 9 plus 18 is 27. Okay? Good? Everybody got 27? Questions at all? Awesome. Okay. Let's let's try one of these ones with the x's in it. I'll give you the other values, right? So number 4 should look like that. Give that a shot. At some point, just write in the values you're missing. We'll skip down and try something that might be a little bit more complicated. Write in the value. Well, you know the values there, I think, right? 3x squared plus 1. Nothing missing there. Let's try that one. So fill in the values for 6 and try and knock 6 out. See what you get. What do we want to do to try to model that? Right, and we're looking for an equation again. Okay, what do you think, Jaden?
375 plus 9 equals 1,600.
Plus 900, right? And so the total for his month was $4,650. So we know whatever expression we're going to use to model how much money he makes, it's going to have to be equal to the total of $4,650, right? And so, right, $375 per car sold again is your sort of trigger that we're going to end up using multiplication in here. It did say C, so we got to use the letter C in here. And maybe that's what you said, and I wrote down X anyway.
I said X.
Yeah, ultimately it doesn't matter, right? But yeah, so we know $375 per car. That means we're going to take the number of cars sold and multiply it by 375, and then we're going to add his base to it. The $900. Okay? Good? All right. Any major issues? Great. Okay. We wrap this up by talking about numbers. Number system. Okay. We have number system, and all throughout history, we've had to create a new numbering system because of different situations that we've had come up. Right. Before we were writing on walls in caves, right? We had to make sure that we kept up with however many, sheep we had, right? And so to do that, we had what's called the natural numbers, right? It's natural to start counting with using the number 1, right? So 1, 2, 3, 4, 5, and then all the way up to however you would count are your natural numbers. Then we started writing, okay? And trying to find ways to represent these different numbers to try to create an infinite number of symbols for all the infinite numbers out there. We kind of became crazy. So we got to a point where we wanted to introduce 0, right? We had to tell somebody that I had 0 sheep. And so we took the natural numbers and we just added the 0 to it, and 0 became a way to as a placeholder, right? I don't have any sheep, but I want to tell my neighbor, I'm going to write a letter to my neighbor and tell him that. So I had to have a symbol for 0. I don't know. Something like that, right? But there's a reason for 0 is to become a placeholder, and we call those the whole numbers, okay? And then we kind of came through and realized that sometimes I added sheep to my flock, and sometimes I lost sheep because of disease or whatever. Somebody stole it. I don't know, right? Yeah. And so we started doing some figuring, adding some, subtracting some, those kind of things. And that's what led us to the whole negative, the idea of a negative number, right? Instead of adding 2 sheep this year, I lost 2 sheep, right? And so I wanted to be able to track. And so we didn't really have a way to do that with the whole numbers and the natural numbers. And so we created another numbering system called the integers, which include all positive and negative whole numbers. Okay? And so again, there's a need, and so we're filling that need by introducing a new numbering system. And so then we've got, all right, great. we're going to start performing a lot of mathematical operations besides just taking sheep, adding sheep and taking sheep away, right? And so we came across another situation. We want to start talking about multiplying, dividing numbers. And with what we had so far, with just the natural numbers, whole numbers, and integers, we didn't have any way to do that. And so we had to create a new numbering system called the rational numbers. And the rational numbers are any number that can be written as a fraction. Any number at all. Doesn't matter. Okay? If you can write it as a fraction, it's called a rational number. Okay? All of these, I'm sure you've heard of before. You may not have gotten to yet is the idea that all numbers are rational. Right? There are numbers out there that are kind of like teenagers. They're irrational numbers. Right? Irrational numbers cannot be written as a fraction. Can't do it. Okay? Example of something like that. 0.25. Can you write that as a fraction?
Yeah.
As what?
Fourth.
Yeah. 1 over 4. Right? So a rational number, right? Obviously, you can throw some negatives in here if you want to. Negative 2/3, that's still a rational number. Even a number like I'm trying to make stuff up now. You need decimal. 0.18 is still a rational number. You can write it as a fraction. I don't know if you remember how to do that, convert decimals to fractions. You remember how to do that? 18 over,
100.
right, because it's 18 hundredths, right? And then simplify it down, which is, 9 over 50. Okay, so it's still rational. What do we mean by irrational then? It seems like any number is going to be a rational number, right? What number cannot be written as a fraction? Right? Pi. What's that?
Pi can be written as a number because it's pi.
Right? Okay, kind of. The problem with trying to write pi as a fraction is that, like we were saying, right? If you can take a decimal and write it as a fraction because this decimal ended. This is 0.18, 18 hundredths. Yeah, pi we haven't found the end of pi yet.
There's still a supercomputer somewhere. Still going.
Yeah. I don't even know how many digits it's up to now, but I'm sure it's in the millions.
Probably past that.
Probably. Right? And so since it doesn't end, we can't put that over a number with a bunch of zeros to represent where it stopped. And so irrational. Pi is irrational. Not the only one. Okay? As a matter of fact, there's something called E that you'll learn about later. There's pi. Really, since we just introduced the idea of square roots, that sort of introduces some irrational numbers as well. Okay? But the idea behind irrational numbers, we cannot write them as a fraction. And this idea of radicals, square roots, kind of gets us into some of those too. Okay? Name the subsets of the real numbers to which each number belongs. Okay, with that in mind. -5 could belong to more than one. Integers, absolutely. It'll fit there. It's a negative number, negative whole number. Right? Any other number set? Right, because you can write it as a fraction, right? Okay. About the other 6. Knock them out real quick, see what you think. Write down what subsets you think they belong to. And check and see if you're right. Okay, got some good educated guesses in there. Here's an easy one. We just talked about number 2, right? Logan, what kind of number is number 2?
I'll put it irrational.
Yeah. For sure. Okay. Any other subsets that belong to? It's not a whole number, right?
Yeah.
So it can't be an integer. Okay. Good. What about number 3? Gary, what do you think?
Natural numbers.
Natural?
Yeah.
Is that the only one?
And also the whole numbers.
Sure. It fits there too, right? Which means it can probably also fit, right? Can you make it as a fraction? Can you write it as a fraction? Sure. Anything else? An integer too, right? It's a positive whole number. Fits as an integer also. Okay, good. Barbara, how about number 4? What do you think?
I did natural number.
Natural?
Yeah.
Okay. Do we count using the square root of 17? You go 1, 2, 3, square root of 17? No, right? Remember our natural numbers is what we used to count, right? It's okay. It's all right. Let's help her out. It's not a natural number. If it's not a natural number, can it be a whole number?
No.
No. If it's not a whole number, can it be an integer?
No.
Right? Remember, if you look at your notes, the definition is positive, negative whole numbers. Can't do that. So the real question is, can you write square root of 17 as a fraction?
No.
No, you're right. The answer is no. So this guy is actually irrational. Okay? Good. 3 over 5. 3 over 5. Right, Zach? Rational, because it's already a fraction. Right? That makes sense. Anything else? Doesn't fit as we don't count with 3 over 5, right? So it's not going to be a natural number. It's definitely not a whole number. Okay, good. And then 6. 6. Caroline, what do you think? What kind of number is 6? Irrational? Can't write it as a fraction? Okay. Everybody okay with that? Because it shouldn't be. Can't write 0.3 repeating as a fraction?
No.
Right, but I understand where you're going with that, right? It doesn't actually stop at 0.33, right? So it's hard to write as a fraction that way. But there's no fraction that's 0.3 repeating.
Over 1.
1/3 is,
Oh, yeah.
right? Remember, 1/3 is 0.3 repeating, right? So it's a little bit of a trick there. This is actually going to be rational. Okay? I gave you the tricky one. That was me. Okay? There's a way to convert it from a decimal to a fraction. If you don't remember how that is, we can talk about it at some other time. But yeah, 0.3 repeating is also 1/3. So this guy's going to be rational. Okay? Any issues there? We good? Okay. All right. Couple more things. Some more vocabulary for you real quick. Right? All right. Distributive property. You guys know what the distributive property is. Some of you guys have already tried to use it. Okay. It's when that number is sitting outside a grouping symbol. So a value is sitting out, not a number, but a value is sitting outside a grouping symbol like B plus or minus C, and the A is sitting outside the parentheses. Distributive means we're just going to do what? What operation are we performing to distribute? We're going to take A and do what to it with b? Multiply, right? So we're going to multiply, right? So boom, boom, boom. Distribute a times b, a times c. Okay, it doesn't matter if that value is in front of the parentheses or at the end. It's the same thing, right? Okay? A term, another vocabulary word for you. What's a term? A term is any number, variable, or the product of a number and one or more variables. Okay? It can be more than one variable. So some examples. 6 is a term. X is a term. 7x is a term. 3xy is a term. Okay? That's what we mean by terms. Okay? A constant. A constant is a term that has no variable, right? May not be the first time you've heard this before. Constant, no variable. Still a term, so it's just basically a number. Any number is a constant. Call it a constant because that's going to be the constant value of that. An x letter we use as a variable. I'm going to call it a variable because that number could vary. Okay? So a constant, we already know what the value is, and it's never going to change. Coefficient is the name that we give a numerical factor of a term. Remember, factors are the things that we're going to multiply together. Right? So the coefficient, a numerical factor of a term. Sort of a short and sweet way of looking at this is the number in front of your variables. Right? So if we got something, if we have a term like 72b, then 72 is going to be your coefficient. Right? Again, these are words that we're going to keep using. We want to make sure that we understand what they mean. Okay? Like terms. Again, not the first time. Anybody not heard of like terms before? Not know what like terms are? Not going to tell me, right? Like terms are terms that look alike, right? They have the same variable factors or the same letters. 3a and 8a are like terms. 4xy and 9xy are like terms. Okay? Because multiplying, we don't really worry so much about the order. 4xy and 9yx would still be like terms. You probably won't run into that a whole lot just yet. Okay, but like terms are anything that looks alike, have the same variable factors. Okay? All right. Then we get to the situation where we're going to try to use these ideas to simplify. Okay? Okay, we got a little bit of time here. Let's do something. Let's just sit here. Let's meet each other. So here's what I'd like to have happen. You guys are working on this, right? Jaden, I'd like for you to go find Logan. Okay. Brooke, I'd like for you to go find Evan. Hunter, I'd like for you to go find Barbara. Gary, I'd like for you to go find I don't know, Spencer. Birgitta, I'd like for you to go find I don't know, Christian. Okay. Rex, I'd like for you to go find. Oh, you already have somebody, right? Or no? Rex, I haven't put you with anybody yet. I'd like for you to go find Emily. Okay, Patrick. If you not here, that's right, because you're sitting in a seat. Sorry. Henry. How about Caroline? You haven't put anybody yet, right? Great. Let's move. Let's get together. Who am I missing? Anybody missing so far? Okay. Jackson, how about you work with Isaac? Okay. So let's go through these real quick. Maybe I assumed too much. Here's what I mean, right? We're just going to simplify. We're going to keep working until we can't do anything anymore. So if I've got this 5 sitting outside of x plus 7, what we just talked about, right? The distributive property. I know that I can distribute that 5 to both the x and the 7. So 5 times x is what? Right. 5 times 7. Okay? No equal sign, so I'm not trying to solve anything. That's all we need. Now, can you take 5x and add 35 to it? 5x plus 35. Can you add those two together? No. They're not like terms. They don't have the same thing. Right? And so I can't combine these two here. Okay? Now, this guy. Doesn't matter if the number's in front or the number's behind. Okay? We're still going to distribute. Boom and boom. Negative 2 times 3b is what? It's negative 6b, right? We're just going to multiply the numbers together. Negative 2 times negative 7. Negative and negative make a positive. 2 times 7 is. So we're just going to add 14. Okay? Does that make sense? Cool? How about the next one? Don't see a number there. It's just a negative sign. What number is really there?
1.
Right. So we're distributing negative 1 to both of these. Negative 1 times positive 4 gives you what? Negative 4y. Negative 1 times negative 5. Negative and negative makes a positive. Right, this is going to be positive 5. Okay? Next one. Same deal, right? Here and here. You're basically, what are you doing when you're distributing a negative? You look back. Yeah. If you look back to number 3, all that really happened was you just changed the signs, right? Negative 1 times negative 21 is positive 21. Negative 1 times negative 5m is just positive 5m because 2 negatives make a positive. So you're just changing the sign. Okay? Now, here's where we may need to talk a little bit, right? You can only combine terms that are like terms. Okay? In other words, I can only combine the 3x and the negative 5x. And when we combine them, we're adding them together, right? So 3x plus a negative 5x. Right. We're just going to use the numbers, right? 3 plus negative 5 is negative 2, so it's negative 2x. Right? And then we can combine these guys. 8 plus 6, 14. Okay? Does that make sense? Just got to be like. It doesn't matter what they look like. They have to look the same or look similar, right? What are your like terms in here?
Girls High School, just a quick announcement. This message is for any student driver. So if you are driving to school, please listen. Starting today in both of our parking lots.
Okay, so these are your like terms, and we're going to go ahead and just combine the like terms. And again, the like terms are the ones that look alike, right? So the 16x squared and the negative x squared. We're going to combine those. And again, when we combine them, we merge them, we add them. So 16x squared plus a negative 1x squared is going to give you 15x squared, right? And then the 8x and the negative 4x, we'll combine those. 8 plus a negative 4 gives you 4x. And then 7 and 2, add those two guys together and you get plus 9. And again, it's not an equation. We're not trying to solve anything. We just want to get it down to where we can't do anything anymore. And since none of these guys are like terms, we can't combine them. So we kind of stopped there. Okay. Last couple. We're going to combine some things here. First things first is I want to distribute this 4. Right? I do know that this 9x and this x are going to be like terms, but I don't know exactly what the value of this term is, this x term is, quite yet. And so I've got to distribute this 4 to find out what that is. So we multiply and we distribute. 4 times x is 4x. 4 times negative 8 is negative 32. And then we're going to add 9x plus 5. And then now we got our like terms here and here, here and here. Right? So 4x and 9x is 13x. Negative 32 plus a 5 is negative 27. Right? And so there we are with our like terms. Okay? Last but not least, number 8, real quick, I'll show you that. Again, we want to distribute. There's this negative 1 sitting outside of here that I want to distribute into here. And in essence, that minus sign, 5 minus that, we can treat like a negative sign. Right? And carry that with a negative 1. So when we get that, we get 5. Well, negative 1 times 2x is negative 2x. So negative becomes that minus sign. Negative 1 times 5 is negative 5. And we got plus 3x. And now we see our like terms are here and here, here and here, and those are the only ones we can combine. So 5 and negative 5 is actually 0. Negative 2x plus 3x is a positive x. Well, hopefully you remember that anything plus 0 is just itself, so 0 plus x is x. We can just leave that as x. So all that mess simplifies down to x. Okay?